Hey, welcome back, chemists. Today we're going to talk about stoichiometry, limiting and excess reagents, and percent yield. So this one is actually going to be a three-parter, so I'm going to break it down a little bit for you all. Okay. To start out with, a recap. So we know how to convert between grams, moles, and particles using the molar mass, which we find by adding up atomic weights, and Avogadro's number, that's 6.022 times 10 to the 23rd. Okay. So molar mass helps us convert between moles and mass. You use the molar mass. And Avogadro's number helps us convert between moles and particles. Okay. We also talk about the mole ratio, which is a ratio showing the relationship between the amounts of molecules and particles in a balanced chemical equation. All right. So stoichiometry here is a branch of chemistry that deals with determining the quantities, also known as the amounts, of reactants and products produced in a balanced chemical equation. Okay. Stoichiometry helps us predict how much of a reactant is needed. So if you're a pharmaceutical company trying to make some medicines, you have to know how much of a particular reactant you need to make that drug. And you also want to know how much is produced. So if we know these quantities, all right, industrial chemists, so anyone working with petrochemicals like gasoline, ethanol, rocket fuel, stuff like that, pharmaceuticals, so common drugs, anxiety meds, things that maybe some of us make use of. And food science, strangely enough, is also just chemistry at a certain level. Can help us determine the material costs and profits of industrial scale chemical plants. All right. We can also get help with environmental chemists to determine how much hazardous waste will be produced from a chemical reaction and plans for how to dispose of it. Also, when will it reach a toxic level in the environment? All super useful information. All right. We can also use stoichiometry for all chemists to make efficient use of resources. Okay, we have a limited number of resources on our planet, and so we want to figure out mathematically what is the best way to use these quantities, all right, as reactants and products to produce chemicals that we need. Now, for example, I've actually got a piece here of argentite, all right, which it gets its name because it has the chemical argentum in it, which is actually just the element silver. All right, so its Latin name, argentum, gives it the argentite name. So let's say there's a silver mining company in Argentina, which is named because it has a lot of silver there, is refining silver sulfide, so a crystal like this. All right, I might actually do this at some point, to produce solid silver, which is very valuable, and solid sulfur, also very valuable. And they want to determine how much profit can be made from opening a new mine in Argentina. Right? So I'm going to give you this simplified equation that represents how they refine silver sulfide. Right? It's way more complicated than this, but basically you take some silver sulfide, some of this stuff, and you turn it into silver and you turn it into sulfur. Okay? So this is the balanced chemical equation for it. So sulfur actually comes in eighths, which is kind of odd. Okay? So this is our balanced chemical equation. Now, let's say the mine contains 8,000 grams of silver sulfide, so 8 kilograms. How many grams of solid silver can be refined from 8,000 grams of silver sulfide? Okay, so we're going to start with 8,000 grams of silver sulfide, so that's our start, and we want to end with grams of solid silver. So this is our goal here. Okay, now remember these stoichiometry problems. We have 3 steps that always help us. Okay, identify what are the starting units. Are they grams, moles, or particles? We just did that. And our desired end units, grams, moles, or particles. We just did that. We're going to go from grams to grams. Second step, if we don't know moles, always convert to moles as the first step. Moles is the center of everything. All right, we can go anywhere from moles. Then we'll decide our next steps based on our current units. Okay? Now, in order to go further in chemistry with stoichiometry, we need to expand our flowchart to include more information. Okay, so we want to go from grams to grams. That's exactly where we are, right? But notice we're not going from grams of silver to grams of silver. We're going from grams of silver sulfide to grams of silver itself. Okay, so this is where the mole ratio comes in handy. But first, let's make some space. All right. So we're going to go from grams here to grams over here, going from grams of one chemical to grams of a separate chemical. Okay. So in order to do this, this is why we learned the mole ratio. We know using the mole ratio how to convert between moles of one thing to moles of another thing. All right. So that's the goal here. Okay. Now, let's chart our path. we are starting with grams of silver sulfide. That's AgS. AgS is our starting. We want to end with some unknown amount of grams of silver. We want just the silver. Okay. Now, in order to get there, all right, let's trace our path. We'll first have to divide by the molar mass of AgS. Then we will have to make use of the mole ratio to convert from moles of AgS into moles of silver. So now we're on the bottom half of this diagram where silver is. Then our last step will multiply by the molar mass, right? Not the same molar mass that we used up here. Okay, so we'll divide by the molar mass of AgS, silver sulfide, but we'll multiply by the molar mass of just silver. Okay, so this is our path that we charted. Okay, so let's run through this example. We know we want grams of silver in the end, all right? So that's our end goal. And our starting goal is grams of silver sulfide. This is where we started from. I'm going to show the conversion bridge at the top, and I'm going to show the non-conversion bridge method down here, all right? This will help us see how useful conversion bridges are, okay? So our first step we decided on was to divide by the molar mass. So what is the molar mass of silver sulfide? All right, we'll have to take the atomic weight of silver, which is 107.87, plus the atomic weight of sulfur, which is 32.06. So we find the molar mass by adding up the atomic weights of all of the elements involved in this compound. And we get 139.94 grams per mole. All right, so let's put that in there. So we are dividing by 139.94 grams per mole. On the conversion bridge side, right, if we want to divide by something, we just put it in the bottom, right? So it's being in the bottom, it's being divided. Now, let's clean up the units a little bit. That mole can move to the top, okay? So remember, dividing by something in a fraction, we can multiply by the reciprocal. So we'll multiply moles and divide by 139.94 grams. All right? Our second step is that mole ratio. Well, hold up. We have to figure out what our mole ratio is first, okay? So we got this balanced chemical equation. What is the ratio of AgS to Ag? Well, as it turns out, it's just a very simple 8 to 8 ratio. Okay. Now you may be wondering, how do I know which one goes on top and which one goes on bottom? And then this part I ask you to consider, all right, AgS, do we want that as a final unit? Do we want that over here? No, we do not want AgS as our final unit. So this one has to go on the bottom to cancel out with this AgS over here. We do want Ag as part of our final unit, so this one has to go in the top. We have to keep this one, all right? And that one has to end up at the end over here, okay? So we use our mole ratio, all right? Now our final step is we're going to multiply by the molar mass. Not this molar mass. This is the molar mass of AgS. We want the molar mass of just Ag, all right? The molar mass of just Ag is actually right up here. It's its atomic weight, same thing. All right, 107.87 grams per mole. Let's clean up the units a little bit. We can move moles into the bottom, okay? So now we have our full bridge done, okay? And we can check that we set it up correctly for the bridge version, not so much down here. It's a little trickier to check down here. But let's cancel our units, okay? Grams cancels with grams, perfect. AgS cancels with AgS, all right? This is what I was saying. This is how we know this one goes in the bottom, is we want to cancel this. We don't want this as part of our final answer. We have to get rid of it. That's why AgS goes in the bottom down here, okay? Also, moles cancels with moles, all right? So our current final units is Ag and grams. Oh, look, grams Ag. That's exactly what we want. So we can check, and we know that we set it up correctly because our final units match up with our end goal, all right? Now, you'll take 8,000 grams times each thing in the top, and then divide by each thing in the bottom. All right, if you want to do these in steps, you can, or if you want to do it all one row, all the other row, that also works. If you're using this method, you can do it just as it's written out. So 8,000 times moles divided by this, times this divided by this. So 8 divided by 8 is just 1 anyway, so this step doesn't necessarily matter. And then we multiply by the final molar mass. All right, when we do this, we get a final answer of 6,166.6 grams of silver. That sounds pretty good, all right? You get the same if you do it without the conversion bridges, but I strongly urge you to learn this method so you can double check your answer. Do my units all cancel? Do I have my desired units of silver and grams of Ag? That's exactly what I wanted, okay? Now, let's say for example 2, all right, when you refine the silver from silver sulfide, from argentite, you also want the sulfur. Sulfur is a very useful chemical for making sulfuric acid, which is the most produced chemical in the world, the most sold chemical in the world. Okay, so let's say we got those 8,000 grams of silver sulfide again. How many grams of solid sulfur can be refined? Okay, so our start is our grams of silver sulfide, and our end is our grams of solid sulfur. Okay, I'm going to show you this diagram again. Again, this is very helpful. Not going to be available on the test, but is very helpful for you to remember and learn how to do these problems. Okay, we are starting in grams of silver sulfide. Again, same amount, 8,000. All right. Now, our first step to get towards grams of solid sulfur down here is we're going to have to divide by the molar mass. Again, same exact step here. All right. We will get to moles of silver sulfide. Then we have to use the mole ratio in order to convert between moles of silver sulfide and moles of sulfur. All right. This is how we get to moles of sulfur. And then the last step will multiply by the molar mass, not of silver sulfide, but of sulfur itself. All right, we're on the other side of this diagram now to get back to grams. All right, grams of sulfur now, not grams of silver sulfide, grams of sulfur. Okay, so same thing as before. Let's set it up. Let's double check what we got. Okay, we start off with grams of silver sulfide again, exact same start. This time though, we're looking for grams of sulfur, which is S8. It comes in eighths, which is kind of odd. All right. First step, divide by the molar mass. All right. The molar mass of silver sulfide, exact same. The atomic weight of silver plus the atomic weight of sulfur. 107.87 plus 32.06 gives us 139.94 grams per mole. Okay. Now, I am again showing you the conversion bridge method on the top, and I'm the regular version on the bottom to help you see why this is such an important skill. All right. We can switch that moles over, all right? Remember, if we're dividing by something in the bottom, we can switch it up to the top, okay? So the 8,000 grams divided by 139.94 grams per mole, okay? Now we have to use the mole ratio, a little different this time. Here's our balanced chemical equation. We have 8 silver sulfide, gives us 8 silver plus 1 S8, 1 solid sulfur molecule, okay? So our ratio is actually now 8 to 1. Okay. Again, how do I know that silver sulfide goes on the bottom? It's because I don't want this in my final answer. I want S8 as my final answer, not silver sulfide. It has to go, which means I have to cancel this unit at some point. It has to cancel itself out so it does not end up in our final answer. Okay. Now, in this final step, we're going to multiply by the molar mass, right? The molar mass, not of silver sulfide, but of sulfur, which is S8. Sulfur is 32.06 for its atomic weight, its molar mass, but there's 8 of them together. So you take 8 times that, you get 256.48 grams per mole. Let's switch that moles into the bottom, okay? And now we have everything set up. Let's check, let's double check. Did we do it correctly? All right, grams cancels with grams again. AgS, silver sulfide, cancels with AgS. All right, works out perfectly. It's not part of our final answer. And moles cancels with moles. So the only units we're left with is S8, that's sulfur, and grams. So grams, S8 is exactly what we wanted. That's exactly what we end with. Very difficult to see down here what our units are at any given time. All right, very difficult to see. Okay. When you do all that math out, all right, multiply by each thing in the top, divide by each number in the bottom. So 8,000 times 1 times 256.48 divided by 139.94 and divided by 8 will give you 1,832.8 grams of sulfur, S8. All right. You get the exact same thing on the bottom, but you don't get that bonus of being able to double check your work. Okay. All right. So let's talk about the law of conservation again. All right. Matter and energy cannot be created or destroyed. They can only change forms and location. Can't get rid of it, can't create it. Let's ask, was matter conserved during the refining process? Okay. So we started with 8,000 grams of AgS, silver sulfide. We now have 6,166.6 grams of silver and 1,832.8 grams of sulfur. All right. So if you add these two up, all right, you add the masses of your two products up, you get the mass of your starting reactant again. Now there was a slight difference because I rounded a little bit, but overall we got 8,000 grams as our final answer. So yes, matter was conserved in this case. Okay? And this is why stoichiometry works, is we know matter has to be conserved. That's how we know all these numbers work out, is because they have to, all right? That's the law of conservation. All right, so this is part one. I know it was a little long, but you did it. It's great. Take the checkpoint quiz when you're ready. See you later, chemists.